For this week's lab, we were looking at magnetic forces and wires, using what we have learnt from the last few weeks about magnets and magnetic fields. This includes how bar magnets work, with bar magnets consisting of a north and south pole, with like poles repelling and opposite poles attracting each other. We know that magnetic fields are created by moving charges, and that any charge that moves through an external magnetic field will experience a force. We have also learnt that to determine the direction of a magnetic field, you can use the right-hand rule with your fingers wrapped in the direction of the conventional current. For our experiment this week, we were asked to build an electric train using just two magnets, a battery, an uncoated copper wire, and a plastic tube. We were forbidden from using the internet for the first 20 minutes, so we definitely had to think hard about how we could achieve this experiment. My group, basing our experiment off of web assigned questions we had completed and information we had gathered from the textbook, we decided to begin by coiling the copper wire around the plastic tube until it was all in neat, tight coils. After this, we took it off the plastic tube as we knew that we needed the interaction between the conducting copper wire and the magnets and battery to allow for some sort of electric train to form. We spent a while thinking what actually would be the train, whether it was just the magnets with the battery tied to the ends of the copper wire, or if it would be the battery, or if it would be both. Luckily, we were helped by Johnny, who informed us of a very important fact, that the surface of the magnets is conductive. After this, we were able to realize that we had to place the magnets either side of the battery, as this would connect the battery terminals to the copper wire, making between the battery, magnets, and copper wire a magnetic field in the near vicinity of the battery. We then placed the train that we had made inside the copper wire, where it began to move through the copper coils to the other end. After playing around with the magnets and train for a while, we came to some very interesting realizations. When the bar magnets were placed facing opposite directions, the train would move around the wire, but only in one direction. If just one of the batteries were switched around, meaning that the batteries were facing the same way with opposite poles closest, the train wouldn't move at all. If both of the magnets were flipped, meaning different poles were now closest together, the train would move in the reverse direction. We discovered this particular fact by realizing that the train would be either pulled into or pushed out of the coil, depending on what way it was inserted. The explanation behind this revolves around the different directions of the repulsive and attractive forces on the magnets. As can be seen in the picture, if the magnetic field was facing to the right, as the copper coils were wrapped in an anti-clockwise direction when looking from the right, the battery would essentially have a south and north pole, meaning that when the magnet was positioned with two of the same poles closest on one end and two different poles closest on the other end, both of the resulting forces would be to the right, meaning that the train would move rightward through the copper wire, with the magnetic field moving with the magnets and battery through the wire to allow for the constant motion of the train to occur. So if the magnets were both reversed, the resultant forces would both be in the opposite direction, allowing the train to move, but to the left. And if only one force was reversed, the magnets would be pulling and pushing in opposite directions, not allowing the battery train to move. Therefore, if the direction of the coils of the copper wire were changed to clockwise, the direction of the magnetic field would switch to the left, and so would the relevant directions of the train. We also found, after difficulty with getting the train through the copper coils, that when the coils were wound more tightly, the train moved quicker due to the increased strength of the magnetic field. This would also occur if a higher voltage battery was used. The name given to this electric train concept is a solenoid, where a solenoid is a cylindrical coil of wire that has a small diameter in comparison to its length, and that when an electric current flows through this wire, the solenoid will generate a uniform magnetic field that is similar to that of a bar magnet. The magnetic field strength can be found by the following formula, which takes into account the number of coils in the wire, the current flowing through it, and the length of the solenoid. As this was a bit of a different lab today, there were no uncertainties in relation to our experiment, but more so a range of independent and dependent variables, as just described, that affected the outcome of the electric train. Overall, this week's lab experiment was highly informative and allowed us to get a greater grasp of the concept of magnetic forces and how bar magnets and their attractive and repulsive forces work.